Deep Learning Part 4 Backpropagation. Gradient descent needs the gradient, the slope of the loss with respect to every single weight in the network. For a model with millions of weights, computing that slope looks completely impossible. This is the algorithm that makes it not just possible but nearly free. It is the true engine of deep learning, and by the end of this video, you will understand it completely. Let us state the challenge exactly. The loss sits at the very end of the network. A weight we care about sits near the beginning, buried under a long chain of operations. We need to know how much would the loss change if we nudged that one deep weight. That is a single partial derivative. And we need it not once but for every weight simultaneously, millions of derivatives for a single step of training. That is the mountain we must climb. The obvious approach is hopeless, and it is worth seeing why. Take one weight, nudge it by a tiny amount, run the entire network forward, and measure how much the loss changed. That gives you one derivative, but it cost you a full forward pass through the whole network. Now multiply that by 1,000,000 weights, 1,000,000 forward passes for a single step of descent. It would take an age. We need every gradient from almost no work at all. The key is one idea from calculus, the chain rule. Suppose one quantity feeds a second and the second feeds a third. Then the derivative along that whole chain is simply the product of the derivative of each individual link. Sensitivities multiply. So to find how a weight deep in the network affects the final loss, we multiply the small sensitivities link by link all the way down the chain. Nothing more exotic than that. Take the smallest possible chain to make it concrete. A value z produces a value a and a produces the loss L. Then the derivative of L with respect to z equals the derivative of L with respect to a times the derivative of a with respect to z. Two simple local derivatives multiplied together. Read it right to left. The loss reaches back through a to touch z. That single line is the entire secret of backpropagation. Here is why the chain rule is such a gift. Every operation inside the network is simple, a multiply and add, a sigmoid. And each of these knows its own local derivative, trivially in isolation. Multiplying by a weight w has derivative w, adding a bias has derivative 1. The sigmoid has derivative a times 1 minus a. The whole network is complicated, but every piece of it is easy to differentiate on its own. The algorithm begins by running the network forward, exactly as in Part 2. But this time we do something extra. We keep every intermediate value we compute. Every weighted sum and every activation at every layer is stored. Why? Because those exact numbers are what the local derivatives will need on the way back. The forward pass quietly sets the table, and then the backward pass sits down to eat. Now the heart of it. We start at the loss at the very end of the network and we walk the graph backward. At each operation, we take the gradient that arrives from the layer above and multiply it by that operation's local derivative. That single multiply carries the gradient one step further back. We repeat it operation by operation, layer by layer, until the gradient has flowed all the way to the very first weight, one backward sweep, every gradient. Watch it work on a single neuron with real numbers. The activation came out 0.622, the target was 1. So the derivative of the loss with respect to the activation is minus 0.76. The sigmoid's local derivative, its output times 1 minus its output, is 0.23. Multiply the two and the gradient at the pre-activation is minus 0.18. One final multiply by the input gives the gradient for the weight. Done. That gradient at the pre-activation is important enough to earn a name, the error signal, delta. Delta answers a single question: how much would the loss change if this neuron's weighted sum changed by a little? And here is the beautiful part: once you know delta, the gradient for the weight is immediate. It is just delta times the activation that came in. So backpropagation underneath is really the propagation of delta. Now scale it up from one neuron to a whole layer. The deltas of one layer are computed from the deltas of the next layer, sent backward through the transpose of the weight matrix. The same weights used forward now route the error backward. And the gradient of the weights themselves is an outer product, delta times the incoming activations. So the whole layer is one matrix multiply going forward and one matrix multiply coming back, perfectly symmetric. Chain two layers together and the full picture appears. Start at the output layer. Its delta is astonishingly simple, just the prediction minus the target. Push that delta backward through the output weights, then multiply by the hidden layer's local slope. And now the hidden layer has its own delta. From there, its weight gradients fall out at once. Every gradient in the entire network from one single backward sweep. Look closely at what just happened, because it is the whole trick. The gradient flowing into a layer was computed exactly once, and then reused for every weight in that layer. Nothing anywhere is ever recomputed. Computer scientists have a name for this: dynamic programming, solving each subproblem a single time and storing the answer. That reuse is precisely why backpropagation is fast, instead of hopeless. And now the payoff in full. The backward pass costs about the same as the forward pass, roughly 1 times the work, not 1,000,000 times. So in just 2 sweeps, one forward and one backward, we obtain the loss and the gradient for every single weight in the network. The problem that looked impossible, that looked like 1,000,000 forward passes, collapses into 2. That is the magic. In practice, you will never write these derivatives by hand. Modern frameworks record every operation as you run the forward pass, quietly building the computational graph for you. Then a single command walks that graph backward, applying the chain rule at every node automatically. This is called automatic differentiation. You write only the forward computation, the part you actually care about, and the entire gradient comes back for free. But a warning hides inside the chain rule. The gradient reaching a deep weight is a long product of many local derivatives. And if each of those derivatives is smaller than one, their product shrinks exponentially with depth. By the time the gradient reaches the earliest layers, it can vanish to almost nothing, and those layers simply stop learning. This vanishing gradient problem shaped modern deep learning. We meet it head-on in Part 5. With the gradient finally in hand, we close the loop we opened in Part 3. Feed each weight's gradient straight into the gradient descent rule. The weight becomes the weight minus the learning rate times its gradient. Every parameter in the network nudged just a little in the precise direction that lowers the loss. The gradient told us which way is down, the update takes the step. And this is the heartbeat of all deep learning. Forward to make a prediction, compute the loss to measure the error, backward to get the gradients, update the weights to improve. Then repeat thousands, millions of times. 4 steps in a tight loop. That loop is how every network you have ever heard of, from image classifiers to language models, was trained. All of it, this loop. Let us watch one complete step from beginning to end. Forward, the network takes the input and produces a prediction. The loss compares it to the truth and reports the error. Backward, the gradient of every weight appears in a single sweep. Update, and each weight shifts a tiny fraction downhill. The very next forward pass will be a little less wrong. Repeat that and the network learns. One elegant detail that feels almost like a reward. When you pair a Softmax output with the cross-entropy loss, the gradient at the output simplifies dramatically. All the messy pieces, the exponentials, the logarithms, cancel against each other. And what remains is just the predicted probabilities minus the true labels. Prediction minus target. The very first delta, the one that starts the whole backward sweep, could not possibly be cleaner. Now hold this picture and scale it up without limit. The exact same two sweeps, forward and backward, run on networks with billions of parameters. The algorithm itself does not change in the slightest, only the matrices grow larger. The backpropagation that trains a tiny 2-neuron network and the backpropagation that trains the largest language model on Earth are the very same algorithm. This one, exactly this one. There is a lovely way to understand what backpropagation truly does. It assigns credit and it assigns blame. The loss was too high, the network made an error. Backpropagation works out precisely how much each individual weight contributed to that error. And then it tells every weight exactly how to change to do better next time. It is a network learning systematically from its own mistakes. Step back now and see what we hold. The complete training engine assembled. Forward propagation to predict, a loss function to measure backpropagation to find the gradient descent to improve. 4 pieces turning in a loop. Everything that follows in this course is refinement upon this engine, better activations, better architectures, but the engine itself right here is finished and complete. So part 4 in one line. Backpropagation applies the chain rule backward through the network, computing the gradient of every weight in a single efficient sweep. The engine is built, we can now train in principle any network we can write down. But whether a deep one actually trains hinges on a small choice at every neuron. Next, part 5, activations and nonlinearity.